Hi everyone. We are deep into Unit 1, Alcohols, Ethers, and Epoxides. I'm done talking about alcohols for now. We're going to move on to ethers. And I put ethers and alcohols together because we're going to see later, not in this video, but in a future video, that we can make ethers from alcohols. Alright, so what are we doing in this video? We are doing ether nomenclature and properties, and there is one reaction of ethers that I want to go over, and that's cleavage of ethers. Okay. All right, so let's start with what an ether is. Ether is a molecule that has an oxygen and a carbon on each side. Okay. A better way to represent ethers is using what's called an R group. Or you could think of it as the rest of the molecule, but also you could think of an R group as an alkyl group. And we have an alkyl group on the left, and we could have an alkyl group that's different on the right, so I'll designate that R and R prime. One example of an ether, probably the most used ether, probably you'll use this in the lab as well. This is diethyl ether. But diethyl ether is the common name. The common name came from just naming the two groups on each side and just putting the word ether after a space. Let me show you the IUPAC name though. The IUPAC name is going to consider one side the parent and the other side the substituent. So they're both ethane chains. If I consider the left side the parent, my substituent includes the oxygen. That kind of substituent is called an alkoxy group. Because it's the oxygen with an alkyl group. So this is not a ethyl group, it's an ethoxy group. And we're going to name this ethoxy for the substituent, no space, ethane. I know I went through that kind of fast. I'm going to list the rules for the next molecule. And the next molecule I want to look at is this one. Yeah, that one. Rule number 1. Find the longest continuous carbon chain that includes one carbon attached to the oxygen. When I get a ether to name, I usually put 2 dots, one on each side of the oxygen, because one of those dots is going to be part of the parent, the other dot is going to be part of the substituent. And let me just write down my rule here. Find the longest carbon chain that includes a carbon attached to the oxygen. So one of these carbons has to be part of the parent. And let me just put here that this is how we're going to decide who the parent is. Number 2, we're going to number the chain from the end closest to the first substituent. This is different. Substituent. This is different than the alcohols. Remember, with an alcohol, the hydroxy group has precedence over the other groups, over the alkyl groups and over the halogens, and we number the chain from the end closest to the hydroxyl group. For ethers, the alkoxy group has the same importance as a halogen and as an alkyl group, and therefore you're going to number the chain from the end closest to the first substituent, regardless of what that substituent is. Okay? Number 3, we're going to name the other group the the substituent that has the oxygen as an alkoxy group. I'm just going to put here locate and name alkoxy. We're going to do other examples, and we'll add more rules if it's necessary, but these 3 rules should get us through most of the types of naming that we have to do for ethers. Number 1, longest carbon chain that includes the carbon or a carbon attached to the oxygen. 5 carbons here. Number the end closest to the first substituent. 1, 2, 3, 4, 5. And your substituent is this one right here. We named this substituent ethoxy or ethyl oxygen. This is propyl oxygen. This is 2-propoxy, no space, pentane. Why didn't we put number 1 here? Why didn't we say 1-ethoxy? Because if the ethoxy group was on the other carbon, the chain's so small, this carbon would automatically be number 1. So there is no such thing as 2-ethoxyethane. But we could have had here 3-propoxyethane or 1-propoxyethane. In this case, it's necessary to locate where the propoxy group is. Now, let me give you an example that's going to test this rule right here. It's the same ether as before, but now I'm going to put a substituent on this carbon, and I'm going to put a chlorine. Longest carbon chain that includes a carbon attached to the oxygen. Okay. It's definitely the chain on the right. Number the chain from the end closest to first substituent. Well, we have a propoxy and we have a chloro. The chloro, if we number it from the right, is on carbon number 1. If we number it from the left, the propoxy will be on carbon number 2. We're going to number it from the end closest to first substituent. And in this case, the first substituent now is chloro. Not because it's first in the alphabet. This is the first substituent because we could get a substituent as lowest number as possible. The first substituent numbering it from the other end would be on carbon number 2. It doesn't really matter the identity, right? It could be any substituent, okay? Except for obviously hydroxyl, because again, when we named alcohols, the hydroxyl group has precedence over any other substituent for the examples that we worked on. Okay, circle your substituents. One chloro, 4 propoxy, pentane. Why don't we try one more before we looked at ethers that have rings in them? Let's do this one here. Okay. I'm going to ask you to pause the video and name this molecule, and then when you're done, unpause the video. Okay. The longest carbon chain, 1, 2, 3. Substituents here and here. We alphabetize the substituents. 2-methoxy comes before methyl, and I think, let's double check. We alphabetize based on METH, O beats Y. Okay? Alright, let me show you an example where we have a ring as part of the ether. Now, I'm going to show you how to name a molecule like this. Okay, so that's a cyclic ether, but actually I should say that this is an ether with a ring attached to it. For me, a cyclic ether means that the oxygen is part of the ring, that the oxygen is within the ring. I'm not going to show you how to name those types of ring ethers. I'm going to show you how to name these types where the oxygen is not within the ring. Okay. This is going to be rule number 4, though. We have to add another rule for this. If one of your two groups is a ring, this is easy. The ring is always the parent. Well, good. The ring is always the parent, and now we have to number the ring. But these two groups, the propoxy and the butyl, they have equal importance. And we could number it 1, 2 or 1, 2. So either way, we get a substituent on carbon number 1 and carbon number 2. Therefore, it's a tie. Okay, we have two ways to number it, 1, 2. When you have a tie and you can't decide which way to number it based on the location of the substituents, then you're going to go by the alphabet. And butyl comes first, followed by propoxy. 1 butyl, 2, oh, did I say propoxy? 2 ethoxy, no space, cyclohexane. Okay. Now, if we had something like this, square. Oh, how about this? Let me just do this right. Let's do a bigger chain. And how about, how about that? We have a ring. The ring is always the parent when it's an ether. How do we number this ring? We could either have this as carbon number 1 or this as carbon number 1. I'm going to choose this as carbon number 1 and this is carbon number 2 because that gives me a substituent on 1, 1, 2 because I have two methyl groups on 1. Okay. If I number it the other way, I would have a substituent on 1, 2, and 2. So do you see how this is the better way to number it, even though butoxy is first in the alphabet before methyl or even dimethyl. Well, methyl. Okay. I'll show you how to name this. This is 1. Oh, no. Once you figured out the numbering, you alphabetize the substituents. 2 butoxy. 1, 1 dimethyl. Cyclobutane, 4-carbon ring. Okay, just remember that when you have a Greek prefix, you alphabetize not based on the Greek prefix, but by the root, M. B, then M, and then the parent. The numbering has no bearing, or the numbering is not decided on the identity of the substituent. The numbering is only decided based on the location. You only use the alphabet when there's a tie. Okay? When you number it two different ways and you get substituents on the same carbons. Is there anything else I want to do? I think that's it in terms of naming. I did say that we were going to go a little bit about properties, and let me do that. You will encounter ethers in the lab, in particular diethyl ether. And diethyl ether again looks like this. Okay, I am using the common name because most likely when you look at the reagent bottle, it will say diethyl ether, or the solvent bottle, diethyl ether. As long as I wanted to go over another common name. What if the substituents are different, or not substituents, the two R groups are different? Let's say we have a methyl and we have a propyl. You're going to alphabetize it and put spaces in between the substituents and the word ether. We have an methyl and a propyl, LM. This is going to be methyl space propyl space ether. Common name. These ethers, both of these, are not miscible in water. And in particular, you're going to be working most likely with diethyl ether to do an extraction. Remember what an extraction is? You have a separatory funnel, and you have two immiscible liquids. Let's put there and there. The ethers are going to be less dense than water, and you'll have diethyl ether on the top then. Oh, another way that you can shorthand diethyl ether is put ET for ethyl groups. You have two of them surrounding the oxygen. Diethyl ether. You know this as the organic phase or organic layer when you do an extraction. And your aqueous phase obviously has water, but it could be acidic or basic or neutral. We'll just call this aqueous. Another ether that you might be working with in lab, though, is an ether that's miscible in water. So this is miscible in water. It's kind of strange, right? Why is diethyl ether and this methylpropyl ether, why are they immiscible in water, whereas this molecule is miscible? It's a little bit hard to predict, especially when you start making rings. Most acyclic ethers are definitely going to be insoluble or immiscible with water. But this one can dissolve in water. And the name of this is THF, or tetrahydrofuran. And that's the common name again. Okay. Why would you be working with this? This one is a common solvent for reactions. Done in the lab. Okay. You may be asked to run your reaction in the lab using THF. Do you know what kind of solvent this is? We discussed types of solvents when we were looking at substitution. Polar, nonpolar, protic, aprotic. This solvent is polar because you have a carbon-oxygen polar bond. Aprotic. It doesn't have a hydrogen or proton to give up very easily. This hydrogen right here is very non-acidic, right? It's off of a carbon. Aprotic. Do you remember what type of substitution polar aprotic solvents speed up? They tend to speed up SN2 reactions. SN2 pathways. I just wanted to mention those two quickly. Not a big deal, just in case you see these in lab. I do want to go over our first reaction, though, in ethers. Oops. Where'd my paper go? We're not going to synthesize ethers in this video. I'm reserving that for its own video. There is only one reaction that I teach my class where we use an ether as a starting material, or let me clarify that, where we use a non-cyclic ether for our starting material. This one right here is a cyclic ether, but we're going to look at other cyclic ethers and their reactions later. Let's discuss the cleavage of ethers. This is reaction, I think we are up to L. Yes, we are. Reaction L. Cleavage of ethers. Okay. Let me give us a fairly standard example. Let's take this ether here. Let's add another carbon. And we're going to use HBr or HCl. Doesn't matter which. Okay. For my class, when I give you a reagent, you're going to assume that you have an excess of the reagent and you will do the reaction as many times as possible. Like for instance, if we had a reduction of a double bond and I had 4 double bonds, if I give you hydrogen and the metal, just assume that you have enough of it to reduce all of them. Look at our molecule here. It's an ether. And we're going to do a cleavage. So you are literally going to cleave both sides actually. Okay. We're going to go over the mechanism so you know exactly how this happens. But when I take my scissors and I cut, when I cleave, I have this piece on the left, the dot, and I have this piece on the right. And that's where your halogen is going to go. So we put a halogen here and a halogen here. Okay. Oh. Just give me 1 second. You see how that's bad? I have to make a bond to the dot like I did here. That's why I think for some of us this looks strange. Dot. There we go. Where did the oxygen go? It left as water. I don't normally ask my class to draw that molecule. I'm only interested when it's filling the products, just in the organic, the carbon and hydrogen containing products. Let me go over the mechanism. The mechanism, you know, or you could deduce based on previous knowledge. But there are decisions that you have to be made. Like, for instance, which bonds to cleave first. Okay? Let me show you how I would analyze this cleavage. You have HBr, and we have an oxygen. We're going to protonate that oxygen first. And this is where we have to make a decision. What are we going to cleave first? Okay, do we cleave the bond on the right or cleave the bond on the left? I think for a lot of professors, including myself, it doesn't matter which one you do first. I think the textbook often cleaves the more crowded side first to make the more stable carbocation. Okay. If I cleave this here without any help from a nucleophile, I'll get a primary carbocation. But this one, I will get a tertiary. And let me show you how that works. See, that's a good leaving group now. It's protonated, and what's happening is, actually, let me put my bromine first. Actually, that's going to leave. And if you follow my arrow exactly what it's telling you to do, it's really telling you to get that carbon on the left naked, right? And we have a plus charge here. And we kicked out what? We kicked out this alcohol. Okay. Well, we're assuming that we have excess reagent, and actually we have a Br right here that we're going to use to attack. What does this look like? This looks like how to do alkyl halide from a tertiary alcohol. Remember? But if you had a tertiary alcohol, you would kick out that as a water molecule and then have the halide attack the carbocation. That takes care of one of our products, right? It takes care of this product over here. But we have excess HBr, and you know this. Alcohols with HBr, you do substitution and you get the alkyl halide. So let's go back to our alcohol chapter or alcohol video, and we could branch off and we could do this. We have enough HBr that we could do both. Put a Br here, but also cleave or substitute this OH out. Remember that OH is not a good leaving group. Okay, hopefully these are all terms that are very familiar. Hopefully this is a mechanism that's very familiar. Right? Primary alcohol plus HBr, the substitution via SN2. SN2 because that's a primary carbon. We're not going to make primary carbocations in this class. And what do we get? Plus H2O. Those are your two products, your two organic products. If you think about what's really happening here, that leaving group left on its own, this is an SN1 process that it gave us a tertiary carbocation. But over here, the nucleophile attacked to kick out the leaving group. This is an SN2 process. Okay. So we're doing two processes because we're cleaving these two bonds. It really doesn't matter to me if you did the SN2 first. Okay. How would you do the SN2 first? At this point, you would have the Br attack this carbon and kick out now this group on the left. Okay. Again, it doesn't matter to me when you draw the mechanism which one you cleave first. Okay. Most textbooks want you to do the one that forms the more stable carbocation first. Now, this is a case-by-case basis, correct? Because maybe you can't make a very stable carbocation. What happens if your ether is like this? Okay, just a very simple two alkyl chains. Well, both carbons are primary. So you're not going to make a primary carbocation. You're just going to protonate and use the halide to come in and attack. Now, does it matter which one you attack? It doesn't matter. Okay, it doesn't matter. As long as you have enough HX to cleave both sides, and which you do. Okay, I'm not going to go through the mechanism, but what if we go ahead and use HCl? What are your products going to be in that case? Again, the trick is you cleave or cut, you use your dotted lines, and we have one piece on the left plus another piece on the right, and you don't have to draw water. But we did make water, didn't we? Where did we make water? Oh, right there at the bottom. Yep. Now there's one example that I want to warn you about, and this ether right here is I'm gonna show you a warning. Let's use HI. Okay, we could use HBr, HCl, HI. You might think that your product is this, your two products. But this is not a product because there's a rule that we learn in Organic Chemistry 1 that you don't substitute at an sp2 carbon. We'll learn ways to do that later, but for now, this will not cleave this bond over here. Okay? If that is the case, what do we have left over? We have the alcohol that when you react with HI, you don't substitute here. You can make this into a protonated OH, but it's still not a good leaving group when it's off of an sp2 carbon. So just beware of that. Your two products here are these two. Now you can, and I'll leave this as an at-home problem, you can cleave this, HI. Okay, because that carbon is not an sp2 carbon. That's an sp3 carbon. You will be able to, when you react it with HI, cleave both sides. Okay. So my time is up. You will do this at home.